So tonight I'm going to tell you about some of our and many other people's ideas about using machine learning to simulate quantum physics. Specifically, so I'm looking for the stick. Here. It was here. Okay, great. So specifically, I'll tell you about what we call physics-driven machine learning, and I will explain about these concepts, so especially about this concept of being data-free and what it means. But before going there, I mean, let me mention that, of course, this class of ideas, this family of ideas, belongs to the much broader setting, the much broader field of machine learning for science. I would like to give you maybe an overview of what I believe are the main interesting aspects of machine learning for science and what are also the main challenges in this field. So why should we learn, why should we interested in a new technology such as machine learning, so a new technology that is born out of essentially industry and is being applied a lot in industrial application? Well, essentially because it has happened a couple of times, or actually many times in the past, that new technological discoveries, so essentially new technological breakthroughs, have also driven new science. So, for example, maybe one of the most well-known such cases is the case of telescopes in 1600 that were invented in the Netherlands, and these telescopes were used by Galileo Galilei to observe for the first time essentially Jupiter's moon, and this gave rise to the crisis of the geocentric model and the birth of modern astronomy. So this new technology that gave rise to new physics. The same is true, for example, for the steam engine that predated the beginnings of modern thermodynamics by more than a century, and also by many other inventions, for example, interferometers, such as the microscope interferometer. So this device, this kind of device that you can see here, that were used later on to study, to do the first observations that led to the confirmation, actually, of, for example, of Einstein's special relativity. So it's clear that new technological advances are of interest even for pure science. One such such technological advances is certainly deep learning. So it's the most famous, if you want, or the most well-known subset of machine learning we've seen being developed in the past decade with a great momentum. For example, if you look at what happened starting from 2012 until the end of the past decade, is extremely impressive because everything happened at a fast pace. And we've seen an improvement in many, let's say, industrial applications or in many applications that was clearly driven by the discovery or by the technological improvements given by machine learning. So, for example, image and speech recognition. By 2012, we already had models based on deep learning that were able to beat previously existing computational methods to classify images, to understand voices, and also the impressive improvements that we've seen in language translation tools. Already around 2016, it was estimated that these tools performed better or at the same level of human translators. And all of these advances are there because of essentially deep learning methods. And there are many other cases, for example, game playing. Let me mention, for example, that in 2016, DeepMind, as many of you might know, realized this game engine that was able to beat for the first time the best player in Go with a deep learning-based strategy. And there are, of course, many more recent advances, but I just wanted to quote this golden decade that also led also to the first developments in the field of science. And these developments have gone from the stage of technological breakthrough to a Nobel Prize in less than a decade, as you know, which is extremely extremely rare in the field of science to see such a fast recognition also of this of a technology that goes again from the stage of pure technology to an advancement that is recognized by the Royal Swedish Academy of Sciences. And definitely the Nobel Prize that was awarded in chemistry this year is certainly a testament of how fast this technology has evolved in the field. So as you know, there's been the Nobel Prize has been awarded to the creators of AlphaFold, who have invented this deep learning method that allows us to predict with relatively good accuracy how proteins fold just using their structure. So this is, again, one case where we can see already that this technology is having a tangible impact in pure science. But we can ask also ourselves, of course, if this technology is going to have a lasting impact on the scientific method, or if you want, on pure science, as some of us like to call it. So as you know, the scientific method is a series of steps that are widely acknowledged, that are widely accepted, if you want, in the scientific community, that are used to establish whether a certain theory, a certain vision of nature that we have, mathematical theory of nature that we have, is actually verified experimentally. And this typically goes through these steps. So essentially, there's first an observation phase and a hypothesis phase. Then there is a prediction phase based on the theory that we have elaborated here. And then there is a very important experimental part where we go in the lab typically and we try to assess whether our predictions are actually compatible with nature. And then there's an analysis of the data that we get typically in experiments, and a verification part where we typically also try to reproduce the experiments that we've done at this step. So this is the standard, if you want, scientific method. And it's clear that machine learning, or if you want, AI approaches are going and are already actually impacting each of these steps. So from the hypothesis making to the analysis of data and to the verification steps. So these are all, if you want, steps where we can see, and we are already seeing machine learning at work. So let me give you an example. If you look at the hypothesis and prediction step, so of course, I had to put an example based on large language models. So in this case, this is Claude, which is one of the main large language models that you can find nowadays accessible on the internet. And I asked Claude, make a bold hypothesis and prediction in physics. So this is the hypothesis, if you want, part of the scientific method. And it went quite along in this idea that maybe there are parallel universes that are entangled, and it also suggested some observations that could falsify or not this theory. Of course, some of this is not entirely realistic, but I mean, this hypothesis, making an hypothesis is something that is already at the level of the current possibilities of these simple models. But I mean, more tangibly, already in the context of protein folding, for example, there are predictions that are made in that context. For example, what is predicted are the structure of the proteins, and these are compared, in this case, with experiments. So this is, if you want, these are these two steps in the scientific method. Sorry. Did there what? Yes. This one, you mean? Oh no, I thought you meant the I thought you meant the AlphaFold. Okay, that's interesting. Then I would be happy to talk. So it's this is the problem with these language models, that they don't always give sources. So that's interesting. But indeed, what I wanted to focus on is the one of the steps that I find most exciting, if you want, in the scientific method, which is the experimental part of the scientific method. So where we go and try to test experimentally whether a theory that we have is compatible with the laws of nature. And one of the interesting aspects of the modern scientific method is that this step of experimental validation in the past, already starting with the development of modern computers, has been more and more replaced, is being more and more replaced by essentially computational experiments. So rather than going in a lab and performing ourselves the experiment or asking somebody to perform the experiment, there are some cases where we can rely on experiments that are performed computationally, so in a computer, and that we know obey the laws of physics that we want to test, and that will allow us also to test a more general theory that we have. So in this sense, we already have a substitution, so a slight modification of the original scientific method, a la Galileo, if you want, or even before Galileo, with a synthetic step where, in some cases, we can substitute reality with a synthetic version of it. So now the question is if we can use these simulations to actually reliably test hypotheses. And this is essentially the kind of ideas that I would like to explore today. So essentially, whether we can use a machine learning approach to devise a simulator we can trust. So this is the key word that I want to emphasize. So not a simulator, or not something that plagiarizes other papers. A simulator we can trust, and that can allow us also to perform such computational experiments that would allow us to falsify a given theory, for example. So the requirements that we can put forward for such a simulator is that it should take as an input, if you want, the specific system that we want to be simulated, let's say an ensemble of atoms, a molecule, or similar, and also, if you want, the fundamental equations that we believe govern this such system, and that we have determined by other means. So typically, we know that matter at a certain scale, for example, obeys the laws of quantum mechanics. At other scale, it will obey the laws of Newtonian mechanics. So we know these, if you want, principles that govern the dynamics or the behavior of matter. And so these are the only two inputs that I want to use for this simulator. And I want, as an output, a physically plausible simulation of the system. So I want something that is, if you want, compatible with the laws of physics. I do not want my ML simulator to hallucinate a solution where, for example, if I throw a ball there, then the ball will start going up and will fly away in the sky. So I want something that is compatible with gravity, for example. And I want this machine learning simulator to be able to give me systematic and statistical error bars. So this is crucial, and I would say is one of the main drawbacks of many of the machine learning methods that we are seeing these days, because obtaining such systematic and statistical error bars is not always easy. And it's, I would argue, however, what we need if we want to trust the simulators, because these are going to tell us how confident the simulator is about the reality that it's predicting. So in this sense, the main requirement that I'm putting forward here is that I want to use only the physical laws, and I want to do what we call sometimes in jargon an ab initio, so from first principles simulation, rather than relying on, if you want, data that comes from other experiments. So I want my little computational experiment to be self-contained and not depend on other data that somebody might have given me. Okay, so the application of these general principles, of course, are much broader than quantum physics. They could be applied to any other field in physics or chemistry. But indeed, today the topic is about quantum physics, and I will tell you about how we want to apply these ideas to quantum mechanics, so to what Antoine mentioned before, so interacting quantum many-body systems. So the main difficulty here can be clarified, I guess, by doing a step back and going back to the equivalent of these many-body systems, but in the classical realm. So if we look, for example, at a box containing a set of billiard balls, and these are purely classical, if you want, obeying the rules of classical mechanics balls, we know that the motion of these particles is fully determined by the initial conditions of the position and the velocities, and at each time we can predict, so we can predict efficiently in a computational experiment, for example, where these balls will go after a certain time. And this kind of simulation can be carried for billions even of atoms of classical particles that are described by the laws of classical mechanics. So for classical mechanics, describing an interacting system can be done in a controlled way even for many particles. Now the problem is that when you go to the quantum realm, even for a single particle, the situation is much more complicated because you have to replace this description based on position and momenta, so position and velocities, with a description that is based instead on the quantum wave function. So the wave function is a function, as the name suggests, that describes essentially the probability amplitudes of finding a given electron or a given quantum particle in a certain region of space. So for example, the square of this function will tell you what is the probability of finding the electron here, there, or in another position in space. So mathematically, we go from a simple description where we only have two variables to a description where we need a function to describe our system. And things become extremely more involved, much more involved, when instead of a single atom, a single quantum particle, we have many of such atoms. And in this case, the wave function that describes the amplitudes of this ensemble of atoms is essentially to be found by considering all the possible possibilities of placing your quantum particles inside this box. So typically, for example, what you could do is to draw little boxes, small boxes inside your big box. And in order to specify at each time what is the state, the physical state of your system, you will need to know what is the probability amplitude of finding, for example, one particle here, and one there, and etc., or one particle here, and there. So you see there are exponentially many, essentially, possibilities of placing these particles in all the different boxes. And if you really want to know, if you have a full knowledge of the system, you need to know all the amplitudes of these different states. So these are combinatorially many for if you want the formula, if M is the number of boxes. And the way I like to visualize this is in terms of storage that would be needed if you wanted to store all the amplitudes of this wave function on a computer. And for example, in the case where you take n of the order of m, so the number of boxes of the order of number of particles, you can convince yourself that to store the wave function of only 25 atoms, you will need essentially the largest supercomputer that we have available these days. And you immediately hit an exponential wall in terms of memory that you need to store the wave function, because around under 30 particles, you will need as many atoms as we have in the universe. So it's really an exponential explosion of complexity. However, something that is crucial is that this exponential complexity is not, a prerogative or an exclusive of quantum physics, but it happens in many other domains of either natural phenomena or, if you want, human-made phenomena. So if you look at the game of Go, so the game where you have white and black pebbles and you have to do something with them, I'm not sure exactly what, because I never played Go. So it has been estimated that the number of possibilities or the number of possible games that you can play here is around 10 to the power of 700. Okay? So this is much larger than the number of atoms we have in our universe. And this is already telling you that this combinatorial complexity, again, is not a prerogative of quantum phenomena, but it happens in many other cases. Still, so yet, as I was mentioning at the beginning, these complexities, or in this specific case, can be, dominated, can be understood by a machine. And the case of AlphaGo, so the machine devised by DeepMind to play Go, is a clear example of the fact that this complexity it's not by itself a bottleneck if you are able to navigate it in a careful way. And indeed, this brings me to what people sometimes call the manifold hypothesis. So it's this idea that this nominal exponential complexity that we see in many natural or, again, human-made phenomena, it might be only apparent in the sense that there exist maybe some more compact ways or some more economical ways of describing this phenomena that does not involve an astronomically large number of degrees of freedom, an astronomically large number of, for example, wave function amplitudes. So to give you a very simple, simplistic example, so think about a planet rotating around its sun. So for simplicity, it's a circular orbit, so I apologize with the president. But so in general, to describe this motion, you will need, in principle, two coordinates, x and y. So essentially where this particle is, or this planet is on this plane. But since this phenomenon has some regularity to it, so it's not a random, if you want, object rotating around another one. So since there is this regularity, we know that actually we don't need two variables to describe its motion, but only one is enough. So this angle phi will describe essentially at all times what the orbit of this planet is. So this is, again, a very simple example, simple-minded example of the fact that because of the regularity of some phenomena, maybe we can live with a smaller description of what happens. And indeed, this is the idea that somehow is at the basis of machine learning. So the fact that we can try to encode, we can try to find, sometimes from data, these more compact representations in terms of a function f that essentially maps this larger space onto maybe a smaller space theta. So essentially, neural networks do this, so they give you a compact representation by reducing the number of degrees of freedom to something that is more manageable and easier to manipulate also with a computer, in a sense. So this brings me now to applying this idea to the field of quantum physics, so to the field of many-body quantum physics, and this is what I call neural quantum states. And this is an application of this idea, of this manifold hypothesis, if you want, to the case of quantum mechanics. So there, sometimes it's called the corner hypothesis in quantum physics. So the idea is very simple, very similar to what I explained before. So essentially, we know that among all the interesting wave functions that we would like to describe, we are especially interested, if not exclusively interested, in those wave functions that are solution to these equations that I wrote here. So these equations that I wrote here are respectively with the time-independent Schrödinger's equation and the time-dependent Schrödinger equation. So in other words, the kind of physical states that we want to describe are not random, typically. They are solution to specific equations that have regularity and are not, again, and so for this reason, we can expect that maybe there is only a corner of all possible states that is reserved to physical states. So we can ignore maybe all the rest of these exponentially many, of this exponential complexity, and try to concentrate ourselves only on those states that reside in this corner of physical states. And then the main idea of neural wave function, of neural quantum states, is to represent the wave function amplitudes. So again, U square will give me, for example, the probability of observing my particles at a given position in terms of an artificial neural network. So mathematically, as you might know, a deep neural network, this is the case of a feed-forward neural network, is represented by a composition of some linear transformation given by this matrices W, some nonlinear transformation G, again, linear, nonlinear, linear, nonlinear, until you have you reach the last layer in the parlance of deep learning. And the input specifically for this kind of neural networks are the quantum numbers. So for example, in the previous case, this would be the positions of my electrons. So this would give, and by inputting, so the main idea here is that by inputting these quantum numbers, by inputting the position of the electrons, then this neural network would return what is the probability amplitude of that specific configuration, electronic configuration. So it's really a way to bypass the complexity of storing the wave function amplitudes, because we simply have a machine that can compute these amplitudes on the fly. And as Antoine was mentioning, so this year was also a special year also for the other Nobel Prize in Physics, It was also nice to see that he went to essentially to Hinton, who devised the architecture that is written here, the restricted Boltzmann machine. And this was, in fact, the first architecture that we used to represent quantum wave function. So it's one of the easiest neural networks that you can devise in the field. These are called the restricted Boltzmann machines because they essentially look like a Boltzmann distribution. So specifically in the case of a wave function, you can see that this takes the form of a Boltzmann distribution, so the exponential of something that looks like an energy, right? So e to an energy is typically found in the Boltzmann distribution in thermodynamics. And in this case, this effective energy that is introduced in these models contains interaction between what we call the visible spins and the hidden spins. So where the visible spins are the inputs to my neural network, and the hidden spins, so the reason why essentially these two gentlemen won the Nobel Prize, encode the correlations among the visible spins. So this is one of the simplest model where these hidden variables, so these hidden features, already encode some non-trivial correlation among our physical or visible or input variables. And then in this representation, we have these parameters, so the interaction strength between visible and hidden, Wij, the fields B and A, and those are all variational parameters, so they are parameters that we can change in order to optimize or to train, if you want, our neural network. And in this case, you can show that by increasing the number of hidden units, you can also increase the accuracy. And the representability theorems tell you that if M, so if the number of these hidden units is large enough, you can encode, in principle, all complex functions that you can, all realistically complex functions that you want to represent. People have studied also how these constructions carry along to the case of quantum wave functions. So after we introduce this kind of representation, so for example, it has been shown that you can represent with a deep neural network, for example, a convolutional neural network such as this one, states that satisfy the so-called volume law the volume law entanglement, so the volume law entanglement. So essentially, you can represent states that have an entanglement that scales like the volume of the system. And also, it has been shown that there are some interesting phases that can be found or can be conjectured to be found experimentally, for example, topological phases. And all these phases can be represented with compact neural networks of the form that I showed before, or of the more complex form based on deep networks. Now, the last, if you want, ingredient that we need at this point is how to make physically plausible simulations, right? So I promised you that we have to try to trust our machines as much as possible. So we have now a representation of our reality that is based on a neural network, but we still cannot trust it with our life, if you want, right? So we have to find a way to make this thing trustable as much as possible. So the idea is to enforce or to try to convince these neural networks to follow the laws of physics as much as possible. And if you want, the way we have to do this is through one of the oldest approaches to quantum physics, to solving the equations of quantum physics, which are variational principles that are found everywhere in physics, actually, and mathematics. So, for example, if you want to solve the time-independent Schrödinger's equation for let's say, the ground state, so the state with the lowest energy is 0, so psi is now my unknown, and E0 is also my energy that I'm trying to find, then you can show that the expectation value of the energy over a given wave function that is parameterized by some parameters theta is always greater or equal than the exact energy. So if you want, we have now transformed this original eigenvalue problem, for those who can read this equation, into an optimization problem, because we can transform this into a problem of minimizing this object here. And minimizing an object through, for example, gradient descent is typically what machine learning techniques are good at. Okay? So we have a way to rephrase this problem into a problem that is intrinsically suitable for machine learning. And the same is true also for dynamics, where, for example, you can show that solving the time-dependent Schrödinger's equation can be rephrased with a variational principle where you have to essentially stationarize what we call the action that is written there. Now, once we have this representation, what we can do is that we can probe them. So fixing, for example, at fixed parameters in this neural network, we can sample essentially this neural network to generate many different possible states for our quantum system. And from these states, we can estimate, for example, the energy for this value of the parameters. And after we have done so, we can also estimate the gradient of the energy with respect to such parameters. And by following, again, by doing gradient descent, essentially, we can minimize the energy and optimize the energy to possibly a value that is close to the exact value, E0, that we don't know a priori. So more technically, this is in the field of the so-called variational Monte Carlo, so I will just flash the technical slide here. But the ideas of the technical detail that you need to know is that we can rewrite this expected value of the Hamiltonian, or as mathematicians call it, the Rayleigh quotient of the Hamiltonian operator H. We can rewrite it in terms of a statistical expectation value over this distribution psi squared that is parameterized by our neural network. So we can rewrite this as a statistical expectation value, and then we can estimate this expectation value using, for example, Monte Carlo techniques. So this is the main trick that we are using here. So we have a Monte Carlo technique to have a statistical evaluation of this, and also of the gradient of the energy that we are going to use to optimize it. So in these final minutes, I would like to give you some ideas of how all of this is being used in applications, because at the end, what matters in the most machine learning approaches is how they're being used in applications rather than, in some cases, their theory. And in this case, I would like to highlight a few cases where we have seen success in using these ideas to simulate quantum systems. So one such case is the case of strongly interacting spins. So essentially, this is an idealization of what happens in a solid, for example, in a material, where you have your electrons sit at some lattice positions, for example, if you have a crystal, and you neglect the fact that these electrons can move around. So they are frozen at these, if you want, at these crystal positions, and the only degrees of freedom that are left are the spin, the internal spin degrees of freedom of your electrons. So these are very important models because they allow you to have a minimal description of why some materials are magnetic, for example, or not. And however, despite their apparent simplicity, these kind of models are very challenging to solve in, for example, 2 and 3 dimensions. And existing techniques typically struggle to provide exact solution to this kind of models. So one such problem that we studied is the problem of the J1 and J2 Hamiltonians, which is written here. So this is a 2-dimensional model where you have interaction between spin sitting on a square lattice. So essentially your spins now are sitting here and here and here and here, and all over the square lattice. And then you have interactions, magnetic interactions at first neighbors, so J1, and also at second neighbors. So what has been shown in the past year, so these are from results from this paper here, is that by increasing the number of parameters in your neural network, you can reach, in some cases, levels of accuracy that are close to machine precision. So this is the case where this term is absent and where we can still find the solution of the model with other approaches. And in this case, you can see that as a benchmark, you can, so we have the exact energy, so we can compare the exact energy, and you can get up to 10 to the minus 7 by increasing the number of parameters in a convolutional neural network. So this is the error you commit. This is the number of parameters when you grow the neural network. But the interesting thing happens when you add J2, and this is the case that we cannot solve anymore with other approaches, and where we have to rely exclusively, if you want, on variational methods to have a consistent comparison. And in this case, you can see that when you increase the number of parameters, you see a similar phenomenon. So in this case, it's the energy. We don't know the error because we don't have the exact energy to compare against, but we can plot the energy, and we know that the lowest the energy, the better is, in principle, the approximation that we have for our ground state energy. And you can see that we can go down by increasing the size of the network until to a point you essentially converge. And these kind of approaches typically also improve on other methods, for example, those shown here, that do not necessarily use neural networks. We have used this kind of approaches also to three-dimensional materials, so three-dimensional spin models, so of the same family. For example, these are spins that reside on these kind of lattices that are known as pyrochlore lattices. They have essentially this shape that you can see from this image. And here, one of the open questions was what happens to materials that are described by the same family of Hamiltonians that I was discussing before. And with the help of these machine learning-based approaches, we were able to identify a region where people were thinking that would be a non-magnetically ordered phase, a so-called quantum speed-liquid phase. But we were able to significantly shrink, if you want, this region, so to the point where we are uncertain about the overall existence of such a phase. So, and in this sense, these approaches allowed us to, if you want, to improve or refine existing predictions to the point where we can really nail down a tiny region of the space of this Hamiltonian where we think this non-magnetic phase could exist. Then, I mean, moving again towards a more realistic description of nature, we would like to unfreeze our electrons in the lattice and have them move around. So this is the case where we try to describe now our itinerant electrons, if you want. And this is even more challenging than the case of spins that I described before, because there is an extra complication that comes from the fact that the wave function that you need to describe in this case must be antisymmetric. So this comes from the so-called essentially Pauli exclusion principle. And the idea is that the wave function, when you exchange the positions of two electrons, must acquire a minus sign here. Okay? So this is an intrinsic symmetry of nature that you have to respect also in your neural network. And it's something that is completely atypical. So it's not something that you find in applications with cats and dogs or when you play Go with a machine. So in none of these applications, of course, you have to enforce somehow that your neural network has to be antisymmetric. So it's also one of those cases where we had to invent, or we have to create new ways of enforcing physically driven constraints that are not present in industrial, so to speak, applications. And there are many different ways. There are several different ways to enforce this constraint. I will not go through all of them, but also in honor of our chairman, I will instead focus more on the so-called hidden fermions approach that we developed here at Flatiron. And this is also actually in nice connection with what I was describing before for the restricted Boltzmann machine, in a sense that it is a way to generalize this, if you want, in a sense, these restricted Boltzmann machines to the case of fermions, to the case of electrons. So remember that in the case of spins, so in the case of standard neural networks where you don't have these antisymmetric properties, we had this idea of hidden variables, so hidden neurons that somehow are able to mediate the correlations that appear in your visible or physical variables. So the idea now is that we generalize this construction to the case where my hidden and visible variables are not standard particles, but they are electrons. Okay? So, and this is at the basis of this hidden fermions idea, where we have now a bunch of electrons that sit in this hidden layer, and we have them interact through these restricted interactions with the physical electrons. And this has been used. We've used it, for example, to study the Hubbard model, so one of the prototypical cases of strong correlations in two dimensions, a very hard to solve model. And in this case, we've shown these were still relatively small systems, but that you can improve other variational methods quite significantly. So these are the errors compared to the exact solutions on these small systems. And we believe that this can be used also to study and attack open problems in the field on also larger systems than those that we studied at the beginning. There are many other applications. I will just flash them. For example, to the electron gas. So for those who want to look more into this, they can have a look at the reference before. Also, there have been very important applications to the context of molecules. So in quantum chemistry, in this review, we wrote about the developments that have happened in the field, some of which driven by DeepMind itself, where these neural wave functions have been applied to study molecules. And in most cases, it has been found that you can find a consistent improvement over other approaches that chemists have developed over the past decades. For example, these couple cluster energies that you can see here can be improved by these neural network predictions in the case of this molecule, this cyclobutadiene. But there are many other cases where this happens, where you can improve systematically over these existing predictions. The last application that I want to mention is to the case of nuclear physics. This is the case where now not only we have our electrons going around, but actually what we are doing is that we are adding the nuclei into the game that we were completely neglected, if you want, in the previous descriptions. And what we want to do here is to study essentially how protons and neutrons get along together and how they give rise to the matter as we know it, so to the stability of matter as we know it. This is itself a very challenging many-body problem of a slightly different type than those found with electrons, but still described by, in some limit by the same equations. So we can hope to solve it also with the same techniques that we developed for electrons, for example. And in this case, so in a collaboration with Argonne, we've studied, for example, the nuclei for example, the case of oxygen. So you have 8 protons and 8 neutrons. We studied this in the case of a non-relativistic scalar Hamiltonian. And in this case, you can predict, for example, what is the density of these nuclei, of these nucleons. And you can match predictions obtained with auxiliary field diffusion Monte Carlo, with the difference that this technique now can be extended typically to much larger systems that those you can treat with auxiliary field diffusion Monte Carlo that is constrained by the nature of and the complications of these nuclear interactions in some cases. Also, we studied the case of neutron matter. So this is also quite a fun case because it's we studied what happens when you have a neutron star and you look at its inner crust. So essentially, when you go down inside in this diagram, so the inner crust, which is here, is essentially a soup of strongly interacting neutrons. And in this case, you can find that there is evidence of these neutrons becoming superfluid. So you can see this evidence, for example, from this plot, where our essentially the predictions from neural quantum states give you this is the probability of finding 2 neutrons essentially one on top of another. And this probability is much more pronounced than what a theory that does not include, for example, pairing, so a simple metallic theory, would give you. So essentially we find a pronounced, if you want, the tendency of the neutrons to go one on top of another. That is an indication of the fact that there is pairing in this kind of systems. Now, also at some point I was mentioning how can we trust the simulations, so how can we be sure that the simulations are accurate, so, or in other words, what are the error bars that we can attach to these simulations. So this is a very hard problem in general, but I believe that we've done some good progress in the field, and more broadly, not only in the case of neural wave functions, but for all variational methods. And especially in this large collaboration that has involved already many people from CCQ, we had the goal of finding a metric that would apply, of course, also to machine learning methods that would allow us to have an idea of how off, if you want, are our prediction from from a faithful description of reality that would exactly satisfy, for example, the Schrödinger's equation. So the idea is very relatively simple to understand. So we define an object that we call the V-score that contains the ratio essentially of two quantities. So one is the energy, so the expected value of the energy, so the same object that I described before in this variational theorem. And then the other quantity that appears here is the variance of the energy. So essentially, these are the fluctuations that the energy will acquire when I measure the energy on my quantum system. Now, you can show that if the quantum system, so if the wave function that you have is an exact solution to the Schrödinger's equation, these fluctuations should be exactly zero, because we say that this is the psi, so the wave function, is an eigenstate of the Hamiltonian, so this means that the fluctuations are exactly zero. So this object will be exactly zero if you have an exact solution, and it will be large if you are far from an exact solution. So this will allow us also to classify how well or how bad we are solving a given problem, and also to have a relative ranking of the difficulty of given problems depending on the value of the V-score that the best techniques that we have can achieve. So for example, if a given technique allow us to, the best technique that we have for the triangular lattice, let's say, allow us to have this V-score, but on the other hand, the best technique that we have to solve a one-dimensional system has this other V-score, then it's clear that we can conclude, for example, that in general, problems on this specific problem on the triangular lattice would be harder to solve than the problem on a chain. So this allows us to naturally classify the hardness of problems. This is a very crowded slide, but essentially we have a way to classify how hard a given problem is by judging the value of the V-score. Okay. So now, since I took more time than expected, I will just move to the conclusions. And what I want to highlight in my conclusions is simply something that I find especially important. And it's the fact that finally, if you want, we are seeing a phase where there is a sort of normalization of the use of machine learning in science. So we've gone past the initial phase of slightly overhyped, if you want, use of the word and the abuse of the word in the field. But we are seeing now a phase where people are embracing this technique as a normal tool. So this is the keyword that I would like to stress to do computational science. And I think this is important also for the future of the field. And this is driven especially by the fact that there are results that can be trusted, and there are results that are here to last also for the next generation of computational method that we will realize in the future. The biggest problem at the moment, as I was mentioning, is to predict and to attach error bars to the predictions that machines make for us. I've shown you some cases where this is possible, or it's reasonably possible. So this is the case of quantum mechanics, but I believe that doing so more systematically to other applications of machine learning to science is extremely important, and hopefully will happen more systematically in the future. And the neural wave functions, something that I find especially beautiful is that allow you to study matter at very different scales. So, from spins to nuclei to stars, by using essentially the same mathematical and numerical tools, you can study the phenomena that are driven again by very different physics and by different type of natural interactions and phenomena. But again, by using leveraging the fact that neural networks are very powerful at analyzing and understanding to some extent the intrinsic correlation and the low dimensional representations of these quantum systems, we can really use the same kind of architectures to describe, again, this vastly different type of phenomena, and we can do so in a sort of largely unified way. So thank you for your attention.